All right, I have launched a record button, right? So here, just would like to recap with you, with every one of you. This week is week 12 or week 13? Anyone? Yes, Amirul, correct. Week 13. All right. In week 13, we supposed to learn the normalized differential equation. Remember that this part we have learned previously, where we normalize that equation to be dimensionless form. There is no unit at all. All right. Once we normalize it, we can include the common dimensionless parameter like Renault number, Stoffel number, all right, the Mach number. So this part is directly related to the dimensionless analysis. So the dimensional analysis is the core for this topic. From the dimensional analysis, you need to do the dimensional analysis using the Buckingham Pi theorem and the similitude. Remember that the similitude is where you expect the prototype from the model. Right? What is model? The model that I have shown to you previously using the ANSYS or using the SD Flow software, CFD tool, we design by using the CAD model, by using the CAD tool, computer aided design like CATIA, like SolidWorks, like AutoCAD. We produce the 3D design, and the 3D design we need to export to the specific file format. Normally in the SolidWorks, which is solid file, IGS file, you can convert into the to the CFD analysis. So that is the modeling. All right, for those prefer on that kind of topic, CFD, the prerequisite you need to have, the requirement you need to have a very good computer. You need to have a very good laptop. So my advice, you can have i5 and above, and then you need to have the RAM more than 8 GB RAM, and the graphic card could be minimum 4 GB, as well as yeah, you need to have those kind of spec in order to run the simulation, the modeling. All right, so this is very interesting for those venture into gaming. I know many of you like gaming to play Dota. So why not you utilize your computer, utilize your laptop to do the simulation study. For myself, all right, my laptop is a powerful laptop, so I utilize my laptop to install those kind of CFD application and run it. I can see what happened before the prototype. Okay, so this one we have learned previously, the similitude. Remember, we expect the prototype from the model. So in the similitude, we should have the geometrical similarity, we should have the kinematic similarity, and dynamic similarity, right? So we learned about confined flow, which is Renault number dominant. We have the free surface flow, which is gravity dominant. We have the high Renault number, which is the Mach number dominant. Right? Remember the Buckingham Pi theorem? We have step by step. The first step, we need to identify the dependent and independent variable. After that, we need to know the number of pi theorem. And after that, we need to select the repeating variable. Selecting the repeating variable shall consist of 4 rules, right? You should remember those kind of rule. One of them is the selection shall not consist of the same dimension. And lastly, previous class we learned about normalized differential equation. All right, that differential equation is not normalized when we have the dimension. So that means we divide all form with the dimension, and the output of that will have the dimensionless equation. So that is what we call as a normalized differential equation. So as of today, we learn about the internal flow. All right. What do you know about internal flow? Anyone? I would like all of you comment. What do you know about internal flow? Hmm. So what's the internal flow? I need to know your based on your understanding, not on the Google. I don't want you to Google. This is not right or wrong answer. I want to see your understanding only. If you Google, then I cannot test your level of understanding. Okay. Why flow in pipe considered as internal? Yes, definitely. For example, flow inside some medium. Okay, we have side and then we have medium inside. Okay, correct. For example, this is the pipe. You can see, right? This is the pipe. The pipe have the continuous flow from right to left, right? So inside here, when there is the flow, for example, it is steady flow. There is no acceleration, only steady, constant flow, constant velocity. So, what do you think happened inside the internal pipe? We call as the internal flow. What do you think when there is the flow? What will be the changes? Anyone? For example, this is a confined flow, 100% of water. There is no air layer between the air and the water. For example, okay, we have the heat loss. Okay, correct. We have the pressure difference. Mm, okay, yes, as well. We have the pressure difference because of the wall friction. Do we have the friction? The friction of the pipe, the wall pipe. Is the pipe smooth at your house, at your home? Do you think it is smooth? Smooth pipe? Yes, definitely no. Alright, the pipe will not design as smooth as what you can make assumption. Normally, we do the analysis, we do assumption, the smooth pipe. But in real case, there is no at all the smooth pipe. The pipe might be rough, that will create the shear stress. All right, the shear stress can reduce the pressure, so that's why we call as a pressure drop, right? So all those kind of things we should learn in the internal flow. Okay, in the internal flow we have the velocity, because there is move, there is the motion, definitely we have velocity. We have the pressure difference, we have the shear stress, we have the viscosity, which is kelikatan. What is viscosity? When someone asks you, what is viscosity? Viscosity is the resistance to flow. For example, you want to go to someone else, someone hold you back, all right? Someone not giving you go there. So we call as the resistance to flow. You want to resist that kind of pulling motion. They pull you, and then you want to flow. That's why we call as the resistance to flow. So resistance to flow in the fluid mechanics we call as the viscosity. Alright, kelikatan. So in the internal flow, as I mentioned before, there are many parameters involved. One of them is viscosity. All right, do you know viscosity, which is resistant to flow on the incompressible and internal? So this is condition 2. What is incompressible? I want to know your understanding. What do you know about incompressible? Incompressible. Eugene, Naim? Rho not change. Okay, yes. No change in volume. Okay. Yes, basically the correct statement is incompressible is density is constant, no change at all. For example, there is water flow and then the density of water always 1000 kilogram per meter cubic, will not change from point 1 to point 2 to point 2 to point 3. It is constant. So we call as the incompressible flow. Yes, another way is the Mach number. The Mach number, when you calculate the flow, the velocity or the Mach number shall be less than 0.3. That is the magic number. Alright? So when the flow is less than 0.3 Mach number, it is considered as incompressible. So what happened when the Mach number more than 0.3? Anyone please comment? What happened when the Mach number more than 0.3? So what do you think the flow? What happened when the flow is more than 0.3? Please give an idea. What do you think when the flow, the Mach number is more than 0.3? Yes, definitely it is compressible. The flow is the speed of the flow is higher. That means the motion is basically more than 100. So what is the speed of sounds? What is the value of speed of sound? Speed of sounds in air. So anyone? What is the speed of sound in air? Okay, density not sound. What is the speed of sound? Kelajuan bunyi. Speed of sounds in air, meter per second. Okay, what is the speed of sound? Try to Google. What do you think? The speed of sound. Yes, 343 meter per second. Correct. So what happened if the speed of water is 120? So 120 divide with the speed of sound, you will get the Mach number. So what's the answer? You will get, what's the answer? The Mach number formula is local velocity divided with local speed of sounds, which is the velocity I give previous to you is 120 divided with the speed of sound, which is 343. So what's the answer? So the Mach number is more than 0.3. So is it considered as a compressible or incompressible? What do you think? It is compressible. So it is not necessary the water will be the incompressible. If the water flow very fast, more than 100 meter per second, this water will be converted into compressible flow. Right? So far you guys understand, yeah? So In this case, the study of viscosity on incompressible. So that means the flow is very slow, the slow flow, which is less than 100 meter per second, and the flow is internal flow inside the pipe, confined flow. Remember that when the confined flow, which is dominant, previously we learned that when the flow under confined, we have the dominant flow. Which is dominant? Which common parameter dominant? Is it the Stoffel number? Is it the Mach number? Yes, correct. Arif Aiman. It is Renault number dominant, which is viscosity dominant. Alright? Okay. So for example, I give you one scenario. Okay. We have a pipe. We have a human being here. Okay, so many human. Not a human lah. We call as a zombie. Uh, Zombie. We have zombie here, and you are running here. Okay, this is you. Okay, you are not a zombie. You are running. Okay. What happened when you ran? What do you think of the zombie? This is your imagination. When you look at the movie, what happened when you run? What happened to zombie? Is it zombie gonna be static, waiting for you? It will follow you. It will kejar. It will try to catch you. Remember? Okay, it will catch you. So if you move very slow, so if you move very slow, what happened to the zombie? Do you think zombie gonna manage to catch you? For example, yes, definitely. So the zombie gonna eat you. The zombie gonna catch you because you are very slow. So you move very slow, the zombie gonna catch you. So do you think this is resistant to you to flow? This give you the resistance to flow? What do you think the resistant to flow? Is it higher or is it slower? Is it higher or lower for the resistance to flow? So definitely it gives you highest resistance to flow because you already this zombie already managed to catch you. So because you are very slow, so that's why it is incompressible slow motion. So internal flow means once you are very slow, this zombie managed to catch you. So you have very high resistance to flow. So resistant to flow means what is the resistance to flow? As I mentioned before, what is definition? What is the actually resistant to flow? Which is the resistant? So resistant is viscosity. So this is viscosity. So what's the common dimensionless directly refer to viscosity? What common dimensionless? Dimensionless. Renault number. That's why Renault number is dominant in this case. So far you guys understand? Are you okay so far? Why the Renault number is very dominant in the flow of water? Because you have very high resistance to flow. So what happen if you move very fast? Do you think you have resistance to flow? Do you think the zombie managed to catch you? If you if your motion is very fast, definitely no, because this zombie. Do you think this zombie have the fastest speed? It is move like it is very slow motion of zombie. So once you move very fast, you can skip this flow. That means you can go like a smooth flow, right? So the viscosity effect will be very small, so that it is not dominant anymore with the viscosity effect. Okay, so I hope you understand. I give you the example of zombie with the human, all right, in order to show you the dominant effect of Renault number, which is you can see here, it is the viscosity, which is resistant to flow. All right. So in this case, the Renault number is the ratio. Renault number, you can see here, Renault number is the ratio, initial force and viscous force. So here is the inertial force. So what is initial force? Which is F equal to FA. This is the viscous force, right? So it is important when dealing with viscous effect. All right, when the ratio is large. So what is when the ratio is large means this Renault number is very large. This ratio is very large. So what do you think? Is the velocity is increasing or decreasing when the flow is when the ratio is very large? Is the velocity increasing? Yes, the velocity, as I mentioned before, this is you. You are moving very higher speed. So this one will be drop. The mu will be very small. You can see here, initial force dominate viscous force. This is true when there is a short, sudden geometric changes. Okay, viscous effect are important when surface area are large. Okay, okay. Let me give you example. This is a pipe flow, and this is very okay. This is the surface area. Okay, what do you think the surface area? Which one is more? A1 or A2? Which is higher surface area? A1. So A1 is more than A2. So let's say this is zombie. Okay. So this is zombie. For example, you can consider that along the pipe, this is zombie around here. So what do you think of zombie here? This zombie have a social distance 1 meter. Okay, 1 meter constant. Even it is zombie, it is 1 meter as well. So this is zombie. Okay, what do you think of the flow? Which has the highest resistance? A1 or A2? Definitely A1, because A1 have bigger surface area. The bigger surface area will have bigger zombie, right? This zombie will create the viscous effect. It is a pulling you. Okay, if you try to move, okay, you are green. That means you are healthy. You are moving here. So this zombie will try to catch you. So this viscosity is very high compared to here. This is you. And then you try to move. Your viscosity is very small. Okay. So far you guys understand, yeah? What is basically the basic definitions of Renault number related to the viscosity. Okay. Okay, this is what it means. Viscosity effects are important when the surface area are large. You mean if the surface area is very large, there will be many zombies. This zombie will kill you, will try to pull you and eat you. So the surface area, more surface area will have more viscosity. Okay. So remember that in our real life, we have two major flow. We have the laminar flow and turbulent flow. Remember that laminar flow is the flow in very smooth flow. Let me draw to you. Okay, laminar versus turbulent. For example, this is the flow. This is the pipe. The flow is very smooth. You will not see any changes in flow. There is no change in motion. If this is the flow of turbulent, the starting it will flow like this. Are you managed to capture this? Do you understand what is the difference between laminar and turbulent? The flow is very steady flow. There is no change of motion. Even the particle here flow in the same path. Okay? Straight line. This is laminar. Alright. In this case, the laminar flow in the pipe. Alright, this is in the pipe. In order to consider it is laminar, the Renault number shall be less than 2000. For the wide channel, right, the Renault number is less than 1500. How they get this value from experiment? This is done by Osborne Renault. Do you know Osborne Renault is a scientist that discovered this value? Osborne Renault. Why this is called as Renault number? This is after his name, Renault. So this person discovered this flow. When the flow is less than 2000, it is under laminar flow in the pipe. And then the Renault number, the Osborne Renault, curious what happened to the white channel. They conduct a experiment and he found out that the Renault number less than 1500 considered as the white channel laminar flow. Okay, I really hope that you understand until this stage. This is very important. So this is where you consider as the internal flow. So you can see here, we have the entrant flow. Alright, this is flow dalam permulaan, entrant flow. You can see here and developed flow. So entrant flow is at the initial region here. The developed flow is after this region. You can see here, developed laminar flow. In this case, we consider only laminar. Alright, laminar flow. In this region, we consider as entrant flow. You can see here LE. LE stands for the entrance length. And here consider as the developed flow. Alright, so what is actually meant by developed? Uh, develop means something already successful, right? Some things that kind of property will not change at all. It is already developed to the optimum condition. For example, like this part, like this case, this is water. So what do you think of changing here? What's changing the parameter here? Anyone? What do you think of changing here in the entrance flow? The entrance flow is not the developed flow. Yes, correct. The velocity profile. The velocity profile will always change in the entrance flow. It is not matured. Alright, we call as a not matured anymore because it is just a baby. Okay, I can make an analogy like a baby. Okay, this is a baby. Okay. The baby merangkak lagi. Okay. So this baby is under not developed anymore. And after sometimes, a long time, this baby become fully matured person. Okay. So this is considered as a developed flow. So this baby will change. What do you think in this region? What happened to the baby in order to achieve this matured person? What do you think of this baby? Of course, the baby will move. So what do you think of the structure of the baby? What do you think of the structure of the baby? It will move. What is this? This baby try to stand and then fall, stand and fall. And then fall. Okay, so do you, okay, yes, correct. Amirul, this baby is actually merangkak, alright? And eventually after some time, this baby try to move and try to stand until it becomes steady, until it is matured enough. And this can run. So, after the long distance, there is the change of pattern. Can you see there is the change of pattern? This baby, this the first baby, and then there is the change of pattern. The pattern of the baby is trying to stand, and then this is standing, and then it fall back. So this is considered as the entrance, permulaan pergerakan, entrance flow. After achieve certain period of time, okay, this baby become a fully matured that can run 100%, that can walk, stand 100%, that achieve the strength. So same with water. All right, we play with water. The water inside the pipe, internal flow, the first is a baby water. All right, you can see here. However, for the water, it is very, we call as it is so set with the water. We call like this. I play around with the zombie. We have zombie. Okay. What is the function of this zombie? What do you think of this zombie? What is actually the job for this zombie? What is actually the job for this zombie? To give the resistance, alright? To give the resistance to the flow. For example, this is baby. The baby try to merangkak, and then this zombie try to pull until you have the certain strength, you manage to walk and run. So again here, this is wall. Remember that the wall have so many zombie, and this is zombie. This zombie try to pull you, try to give you the resistance to flow. Okay, so initially there is no zombie, and then once you flow, the zombie try to pull you, and then the flow become like this. You can see here we have the viscous wall layer. Viscous means the resistance. So the resistance effect can be achieved, can be filled by the water in this region only. Okay, this region is full of zombie. Maksudnya zombie punya tangan, the hand of zombie. And this is full of hand of zombie. So this one, however, at this region, from this region until this region, dia punya zombie punya tangan until this portion, until this extent. After this region, the hand of zombie full. Okay, so in this case, we consider here as the inviscid core. What do you think of the inviscid? Kawasan yang tak ada, there is no shear. So that means kawasan sini, this area is free from any resistance to flow. Okay, so far you guys understand? This region has no resistance to flow. Okay, so until this part, it finished already, and then continue to this region. This is full of viscous. Viscous effect mean resistant. It's very difficult to flow. So you can see here in the entrance region, separated into two. We have the inviscid length and the entrance length. This is profile development length, right? So this is the structure of the velocity profile. The velocity profile will change drastically, will change in any shapes until it reach this length. We call as the inviscid length. You can see Li. The velocity profile start to develop. We call as a profile development strength. It is still developed. All right, it is still try to move, try to walk, try to stand. So you can see here, this is u with the function of x and y. What do you think of u, the velocity with the function of x and y? So what is x? Which x direction? This is x direction, this is y direction. We look at here. So when there is change of location, the velocity will change. You can see here, if there is change in x direction, is the u will change. This is u with the function of x and y. Yes. What do you think when there is change of y? Suddenly this part have this shape. Do you think the velocity will change? Naim, this is only consider the laminar flow only. Okay, this is laminar. Alright, so that means at the profile development length, the velocity will dependence on x and y direction. After this entrance length, after this length, the velocity profile will not change in x. You can see here, u with the function of y only. This is u with the function of x and y. Is there any function of x here? It is only the function of x. It is only the function of y. So when if there is change of x here, whatever flow, it is always the same. The velocity profile will be the same with this one, will same with this one, will same with this one. Because this velocity profile has not effect on the x direction. Okay, so far you guys understand what's mean by the velocity profile when there is no change in x and y? Okay. So basically, this is about the internal flow. It is very easy, right? Remember that once you open up your pipe, you try to imagine, right? Along the pipe, there are full of zombie with social distance 1 meter, okay? And then the pipe start to flow until at certain extent, the flow become the entrance length. From here to here become the entrance length. After passing through the entrance length, it become developed flow. It is become matured flow. The flow can walk, can run, can stand. Okay. So from here, so you can see with this region, developed laminar flow, the velocity profile cease to change, will not change anymore. Tak nak berubah bentuk. Maksudnya velocity profile tu tak nak berubah bentuk after the developed flow. You can see here, dia punya velocity profile ni tak nak berubah, cease to change. Okay. Okay, this one I have mentioned to you, explained to you further. Alright, this one. The profile developed due to the viscous effect until the developed flow is achieved. Okay, that means this profile, you can see here, this profile try to change its shape like a baby. Remember, the baby try to merangkak, try to stand, try to walk and fall down. This will change as well. This will change until. Okay, do you know why the baby try to walk, stand, and then fall down? Why this phenomena happen? I want to know why this phenomena happen when the baby try to walk, try to stand, fall down. Why? What happened? Why the baby fall down? What's the factor that caused the baby unable to walk smoothly? Yes, correct. Sometimes zombie push the baby, but majority zombie eat the baby. So the zombie pull the baby to eat. Another things, is the baby is the baby have a full strength? Adakah baby kuat lagi? Adakah baby masih kuat? Okay, so the baby don't have any full of strength, so the baby keep falling down, alright? Because of gravity, because of zombie, because no experience. You can see many factors affecting the velocity profile. So in this case, you can see here, we have so many zombies here, and then this baby try to walk. After a certain period of time, this baby become mature and then can walk even there are so many zombies. So that means whatever the challenges happen, this baby can stand all the challenges. That is actually the motivation for you. If you have any, in order for you to grow, to be a successful person, around you will have so many challenges. In this case, it is zombie challenge you. Until you fall down, you move, you fall down, you move up, until a certain period of time, you are no more, you are immune to that kind of zombie, so you can be a successful. So like this, okay. So this case, the profile developed due to the viscous effect. You can see here, the profile start to develop. That means the baby try to develop their strength, even though there is so many of viscous effect. So in this case, the inviscid core, remember that inside here is the inviscid core strength is 1/4 to 1/3, 1/4 to 1/3 the length. They give you the statistic value here. Okay, so how do we determine the entrance? Sometimes people will ask, what is actually the length when the baby try to move, try to become developed? So this is the case where the scientists discover that the entrance length LE over LD equal to 0.065 Renault number. You can see here LE over LD. This is dimensionless parameter or not? Is there any dimension here? L over D. What is the dimension? So it is dimensionless. So many scientists, researchers prefer to place this kind of form, dimensionless parameter. So LE over LD equal to 0.065 Renault number. So if you want to get the LE, the length of entrance, the length of the profile start to develop, the diameter can be multiplied with this number, right? Renault number is VD over mu. This is for the circular pipe. Alright, for the entrance length equation for the laminar flow in circular pipe with the uniform profile at the inlet, Renault number laminar is 2000. So Renault number you already know. For the laminar, it is 2000 in the pipe. For the channel, it is 1500. So remember that rectangular channel, it is like a rectangular shape. You can see here. So it is not using the diameter anymore because the rectangular channel is a square shape. It is a rectangular shape. So they prefer to use the characteristic length, which is the height. So LE over LH equal to 0.04 Renault number. Okay. So far, you guys clear on this? Let me draw. Okay, this is okay. This is the flow, and this is the flow. I think this is not. Okay, you can see we have the heart. We have this flow. Okay, so far you guys understand what I meant by this flow condition in the pipe, in the channel. Okay. You guys okay so far? So, for a large Renault number, okay, we can see here, this is very large Renault number. Sometimes very large Renault number, the flow become turbulent flow. Okay. So this is the case when the large Renault number. Remember that Renault number is the function of velocity. Rho Vt over mu. So higher velocity will increase the Renault number. So highest Renault number in this case more than 10 the power of 5. You need to use this value Li over d equal to 10, Lb over d equal to 40, and Le over d is equal to 120. In this case, this is laminar when the Renault number less than 1500 and 2000. If the flow turbulent, very high speed Renault number, you need to use this parameter, this formula. This is discovered by scientists. So you need to use this parameter. Okay. So in this part, it is the same like previous one, but the previous one is only applied to laminar flow. But this case apply to turbulent flow, higher Renault number. When you talk about what is turbulent, turbulent is a chaotic. The flow is very chaotic and the Renault number is very, very high, which is in this case more than 10 the power of 5. So we have also the inviscid core. We have the profile development region. And then we have the entrance region. And finally, we have the turbulent development flow. The same with the laminar, but for the turbulent, we have an additional LD, which is development length. LE is the entrance length. Li is the inviscid length. If you look at the laminar, we have the Li and the entrance length only. If the turbulent, we have additional length, development length, and then the entrance length. So you need to use this parameter. Okay. You can see LE, LE. For this one, you have Li and LD. So when there are so many zombies, or when the pipe has so many viscosity, what happened to the pressure? Anyone? What do you think of the pressure? Is the pressure drop or rise? Increase or decrease? What do you think of the pressure? Yes. No, the pressure means the tekanan tu, pressure. Actually, the pressure is very high. It means the pressure is the motion of the molecule. It's very, very energetic. When there are so many of resistance, what do you think of the pressure? When there is so many of friction, what is the pressure? Is the pressure from higher will drop or will increase? Yes, definitely. It will drop. The pressure will drop. Okay, for example, you have you open up the pipe at the first initial stage, very high pressure. After very long pipe, after 10-meter pipe, the water will slow or higher in motion. What do you think? The pressure will drop because of the pipe length. Remember, along the pipe, we have so many zombie. The zombie try to pull you down, try to catch you. So there is the resistance to the flow. Definitely, the pressure will drop. Okay. So you can see here, this is the pressure versus the length, x. So the more length, the more x, the pressure will drop steadily. You can see here. However, at the initial x equal to 0, it has a very high pressure gradient. That means it dropped very fast. Okay, this pressure drop very fast from the higher to the lower. The pressure gradient is very high at x equal to 0. Okay, when the transition near x equal to LD, you can see LD here. Okay, the pressure gradient quite small compared to the x equal to 0. So in this case, what they try to mention is this is under turbulent. What happened of the pressure inside the turbulent flow? You can see that when the Renault number of the turbulent more than 300,000, the pressure drop very fast from higher to become here to this point. When this one, this is laminar or turbulent. Transition near x equal to LD. Renault number 10,000. It is laminar or turbulent? This is laminar or turbulent? It is turbulent. Remember that for the pipe or for the channel, pipe is 1,500. For the channel is for the pipe is 2,000. For the channel is 1,500. So it is still turbulent, but the value of Renault number at LD almost 10,000. The pressure gradient is smaller compared to the high Renault number. So that means very high Renault number, the pressure gradient is higher. The lower Renault number, the pressure gradient is still lower. Okay, this is okay. This is the graph, the steadily graph, right? When you can see until when it reach this region, this line, this is become developed flow. It will not change at all. Okay. So here we can see that low Renault number, linear variation begin at end of the transition. Pressure gradient at the inlet is less. Low Renault, pressure gradient less. Okay. This one, this is high Renault number. The pressure gradient is high. Alright. So how do we determine the pressure drop? You must be wondering how we can determine the pressure drop. How to calculate the pressure drop from one point to the another. From this point in the inlet until to the next point. What do you think? What normally what do we gonna use approach or method to determine the pressure drop? How to calculate the velocity profile? So we have in this chapter, we have a special method to address on how to calculate the velocity profile by using the elemental approach. Alright, so we have the elemental approach. You can see here, element. What do you know about element? Anyone? What do you know about element? Element approach. Elements mean. What do you know about element approach? Approach mean method. Cara. Element. What is element? Anyone? What do you know about element? The element, What do you know? Eugene? Arif? Amirul? What do you know about the element? So, the element is where we take one small portion inside the fluid element. So this is the fluid flow. Element means we take only one small portion. For example, we have a pizza, right? Cakap pasal pizza lapar pula. Okay, we have a pizza here. Okay. Biasa normally pizza will cut like this. Okay, so elements mean we take only small portion. Okay, for example, we take out this. Okay, we take out only one small element. Okay, and then we analyze what happened to the pressure at 1, what happened to pressure at 2, what pressure happened at 3. Okay, so what happened to the force, time area. So far you guys understand what is the elemental approach? Okay, after you find all this, you try to integrate. You will find that you will integrate the whole region, and then you will get the final answer. Are you clear so far? The elemental approach, you take only one small portion, and then you do analysis on one small portion. Finally, the result, you try to integrate the cross-sectional area. So finally, you will get the whole solution. So far, you guys understand what is the elemental approach? Yes, correct, Amirul. Elemental approach means you take very small portion. In this case, pizza. You try to solve with the force equation, F equal to ma, F equal to 0, and then you integrate to get the whole solution, which is in this case the pizza. Okay. So same here. We're gonna use the elemental approach for this fluid element. In this case, this is fluid. We take this outside. So you can see here, this is very small. We take it outside in order to know the whole solution. That is the best part of elemental approach. You don't have to analyze the whole. You analyze very small portion, and finally you will get the whole result. Okay, this is what happened. Okay, you can see here, we have the dx here. This is dx. All right, this is distance. D from here to here is x. You can see the origin. This is x, this is y. So definitely this is X. And from here to here, the pressure will act. Okay, I need you to focus on this. It's very important. From here to here, we have the pressure. We have the force. What is the formula of force? F equal to pressure times the area. Okay. So far you guys understand, yeah? I need you to focus 100%. So this is pressure and this is pi r squared. The area of pi r squared is the area of what? It's the area of circle. Okay. So P time area will get the force. So this is the force. So this is the force. Okay, force in this direction. While this is as well is the force number 2. For example, this is force 1, this is force number 2, which is pressure. We call as P plus delta P plus dP, the change of pressure. So this pressure at this point plus this plus dP. Okay, so this pressure plus dP will get this pressure. Okay, that's why you can see P plus dP. Let me zoom. Okay. Yeah, this is okay, sorry. Alright. You can see here. This P plus dP, that means the pressure on the other side. This is P. In order to get this pressure, P plus dP. Pressure on the other side. So what happened to the body force? So we have the force, which is rho G B. Okay. This is the body force. Remember our buoyancy effect. Okay. This term rho time area. Sorry. Rho time area time H. Let me simplify this. Rho V. We have the body force F body equal to rho V, or sorry, gamma V, rho G V. Anyone still remember the body force, which is rho G V? Anyone still remember? I taught you previously. Body force is equal to rho G V. Okay, for those still not remember, you can look at the previous chapter. Alright, so rho G is a gamma time volume. So that's why lead to this equation. So volume here refer to here. Volume is equal to area multiplied with height. So dx is this one, the distance from here, and pi r squared. When you look at in this region, pi r squared means the surface area. This is area pi r squared. So pi r squared is the surface area. Multiply with dx. Dx is this. So definitely you're gonna get You're gonna get the volume, correct? I don't know how to write this. I think like this, yeah. This is dx. So area multiply with dx, you're gonna get the volume. So volume multiply with gamma, you're gonna get the body force, FB. Remember that the volume displaced, right? So actually this one, FB, is directly refer to the weight of the water displaced, which is rho GV. Okay, this is the body weight. And you can see here, this is tau 2 pi r dx. This is shear stress. Tau is the shear stress. This is tau multiplied with area. This is area. So what do you think of the area? Okay, I want you to focus on my camera. Okay, this is okay. 2 pi r. 2 pi r means what? What do you know about 2 pi r? For example, this is the okay. What do you know about 2 pi r? What do you think of 2 pi r? It is this is the basic mathematics. 2 pi r, circumference. This circumference. Okay, circumference. 2 pi r is the circumference. So circumference 2 pi r. And this circumference multiply with dx. For example, from here to here is dx. What do you gonna get? Circumference multiply with dx. What is this? Surface area. So from this, you try to open, it become the surface area. So let me show you this. Okay. Yeah, you can see this is paper. Okay. You try to make like this. Okay. Okay. This one, you can see here, this is 2 pi r, circumference, ukur lilitan. Multiply with dx here, from here to here, dx. Finally, you open up, you will get the surface area. You can see here. So far, you guys understand? Are you okay so far? Okay. Alright. So this surface area multiply with the shear stress, you're gonna get the shear force. This is shear force. F equal to tau A. Alright. So from this case, we apply the elemental approach. Remember that this flow has the velocity. We can apply the momentum equation. And this flow has the force. We can apply the Newton's second law. What is the Newton's second law? F equal to ma. Summation of force equal to mass time acceleration. Okay. So based on this elemental approach, all right, we can apply the force balance. All right, since the velocity profile doesn't change in x direction. So for this case, we talk about the developed flow. Means the velocity profile will not change at all across the distance. It is always the same pattern. So this is only applying for the constant flow, constant velocity profile. Fully developed flow. So we apply this one, the force balance. You can see here, this is the summation of force. Summation, Okay, we apply the momentum equation, which is summation of force in x direction positive equal to mass times acceleration. This is Newton second law. Newton's second law said that when there is the motion with the force, we have to include all the components. So, do we have the acceleration here? Anyone? Do you think this is accelerating? The flow in pipe. No. So, in this case, we are not considering any accelerating component. This flow is constant velocity. So, when the constant velocity area equal to acceleration equal to 0. So this component equal to 0. Then summation of force equal to 0. So what is the force? You can see here. So what is the force? This is x direction. I give you the coordinate. This is x, this is y. Alright, what is the force affecting this elemental approach? So from here, positive, alright? You can see pressure time area pi r squared, which is pointing to the right, positive. You can see another one, pressure plus dp pi r squared, which is pointing to the left, negative. And then we have the shear stress here, right? Tau 2 pi r dx. This is the surface area. This is shear force. And you look at here, we have the body force, which is previously we discovered that the body force FB equal to gamma volume. This is gamma and this is volume. Pi r squared dx. Alright, why sine? Sine is, we want to sine this one because this is horizontal. In order to get the horizontal component of FBX, so gamma V, so this one let me draw like this. Okay. Gamma V, okay, sine, okay, sine theta. Okay, this one sine SOH. Sine theta equal to opposite over hypotenuse. So this is opposite. Opposite is dx. It is half dx. Okay, let me. This is x, and then this is y. Okay. So sine y. And get here. Right. This is component. So in order to get this one, x equal to y sine theta. So you will get this one. Alright. So you need to use the sine in order to get the FBX, x component. So after you use the force balance, summation of force in x component equal to 0. Alright. We use the sine theta equal to dh over dx. Remember that I used before this dh over dx. And then we simplify this equation because the right hand side is equal to 0 and lead to the tau equal to negative r over 2 d over dx pressure plus gamma h. This is the simplified version from the equation 731. You try to divide all these and then you simplify, you move around. Basically, I have done this one from my solution. It is correct. And then we replace tau. Remember, our tau is mu over du over dr. We replace tau with this part. Okay, remember tau is a negative gradient. Okay, so negative with negative we cancel out. After that, we integrate in order to get the velocity profile. So we integrate this one. The viscosity move to the right, and here, okay, dr here move to the other side. You can see here, and dr move to the other side, so become dr. So you integrate both sides, and this is u with respect to r, and then you integrate this one with respect to dr. Finally, you will get this equation. Okay, so far you guys understand? Basically, this is how it derived. Anyone? Okay. This is how we simplify. This is, you need to remember, you only need to remember how to get this one. You need to remember this velocity profile, we call as UR, is the velocity profile with function R. Means there is change of R will have different velocity profile. You can see here, the only variable change is R. R squared minus R naught. What is R naught? R to the wall. You can see here, R naught is the R to the wall. Thus, you can see the velocity distribution in parabolic. This is R squared minus R squared. This is the function of parabolic. And sometimes this is called the Poisson flow. Alright. This one, again, this one we use the Newton's second law to derive this. If you know the Navier-Stokes equation, can also solve this one and lead to this term. You can see the same. This one using the Navier-Stokes equation, and this one using the force balance, which is the Newton's second law. The result is the same. Okay. After you get the velocity profile, you can get the average velocity. So what is the average velocity? V equal to Q over A. Remember, Q equal to AV. So Q is the function of this one. This is area, pi r squared. R is the R naught. You can see R to the surface, to the wall surface, R naught. And here, the Q is the flow rate. Q multiplied with AV. So this is area, this is velocity. U is velocity times area. We get the flow rate. U, this is the function of what we previously managed to get. U is equal to this. We replace in this equation. You can see here, we replace this form and lead to this form. Right? This one after we replace U. This is, remember, this is, okay, this is velocity and this is area. Velocity times area equal to volume flow rate. And in order to get the average velocity, U over area. So area here is pi r squared, cross-sectional area. So this one is the R naught. So pi r squared naught, you can see here. And then this VA is velocity here. You substitute in this equation, lead to this equation. Okay? 2 pi r dr. Okay? Area. And finally, this lead to the final pressure drop. You can see that the final pressure drop, okay, equal to delta P equal to 8 mu BL over R naught squared. This is for the inclined part. For the inclined part, you need to replace pressure plus gamma H. Okay. This is laminar. The pressure drop only apply to laminar. At the end of the day, you only need to remember this. Believe me, you need to remember this only. You need to remember this one, and then this one. That's it. The one that I shown to you previously is the derivation, right? And in terms of the friction factor, all right, the dimensionless wall shear valid for both laminar and turbulent. Okay, this friction factor ni macam is like the strength of zombie. What is the friction of the pipe? So if the friction factor is higher, that means the strength of the zombie is higher. They try to pull you. So in order to get that, this is the strength. Alright? So how I say so? Because you can see here. This is F. The friction factor is the strength of zombie. Alright? Renault number is the function of velocity. Remember? If you move very fast, what happened? What happened to the strength of zombie trying to pull you? If you move very fast, your Renault number is very fast. What do you think the strength of zombie? Very low. Now you can see the correlation. If you move very fast, this is very small. This is like the strength of zombie, the friction factor. So the friction factor, in this case, tau naught is the shear stress at the wall. Remember the zombie location? Where's the zombie location? The zombie location at the wall. That's why tau naught is at the wall. You can see here. R naught at the wall location. This is the strength of zombie definitely at the wall. So tau naught over 1 over 8 rho v squared. So they try to simplify this one in terms of Renault number. Finally lead to the laminar flow in the pipe equal to 64 over Renault number. So you can see the blue color is what you need to memorize and understand. So this is the pressure, the head loss with the dimension of length. Remember previously we derived the conservation of energy where we have the pipe loss in terms of heat loss. So heat loss is actually equal to the pressure drop over gamma, or heat loss equal to, remember previously we derived the pressure, the heat loss, which is heat loss, oh, this is very big, heat loss equal to K V squared over 2G. So now they show you the constant is actually equal to this. So this is what you need to memorize. Yes, correct, Amirul. The previous chapter, they won't expose you this concept. But this chapter, they explain you. The K is actually the force, the friction factor multiplied with L over D. Remember, when you see the question, the friction factor is the strength of the zombie. So what is the strength of the zombie? Which is F equal to 64 over Renault number. This is laminar. Okay. This is only valid for laminar, which is for the pipe 2000, for the channel is 1500. Another way, heat loss. This is proportional to the average velocity. If you have the average velocity, you can substitute 32 multiplied with dynamic viscosity L, the characteristic length, multiplied with the average velocity over gamma diameter squared. This is but the most famous when we talk about the heat loss, we use the Darcy-Weisbach equation. Which is HL equal to F L over D V squared over 2G. I think that's all about this chapter, right? So this is basically the laminar flow in part, right? So we have finally finished on the laminar flow, the next week chapter, okay? So this example, I will record the video as usual. I will post in the e-learning. So that's all about today's lecture. I really hope that you understand the basic concepts of laminar flow in the pipe, where we need to derive the velocity profile from the Newton's second law, which is F equal to ma. So we are using the elemental approach. So after we get the velocity profile, we need to find the average velocity, which is V average equal to Q over A. We substitute the value of Q with the A, we do the integration to get the whole solution. After that, lead to a pressure drop. And from the pressure drop, lead to the heat loss. So from the heat loss, we use the Darcy-Weisbach equation, which is HL equal to FL over D V squared over 2G. Okay, I think that's all about today. Do you have any question? Please let me know. Okay. Anyone? Okay, thank you. All right, my tips for your test 2, please. Okay, Alhamdulillah. Okay, thank you very much for your feedback. All right, for the tips for your test 2, please understand well the Bernoulli equation, how to derive and apply to the device. Secondly is the mass, conservation of mass. And number 3 is conservation of energy. That's all, right? So I wish you good luck and all the best for tonight. Okay. I end my session with Assalamualaikum and thank you very much.
Waalaikumsalam. Thank you, Doctor.
Okay, welcome.
Waalaikumsalam. Thank you, Doctor.